All right, and we're back for part C. Sorry. All right, let's get ready. There are other ways to classify matter besides solid, liquid, and gas. And one of them, which we'll see when we get to the periodic table, will be metals, nonmetals, and metalloids. And another is pure substances versus mixtures. And all of these different ways of classifying matter are important and very useful. So when we're talking about pure substances versus mixtures, I put pure in parentheses because generally in chemistry, whenever we say the word substance, the word pure is implied. So we may call it a pure substance. We may just say substance, but that means pure substance. Anyway, it's a pure substance is something that consists of only one type of atom or molecule, or in other words, there's only one element or compound present. And what it means is all of the particles are the same. Whether it's an element or a compound, or whether it's atoms or molecules, all of the particles in the sample are the same. So that's what we mean by pure substance. A pure substance will have constant composition. That means that the properties are the same throughout the sample. So the properties, if you have it in a jar, the properties are the same at the top as they are at the bottom, as they are in the middle. The properties are the same everywhere. And it'll also have the same properties as any other sample of that substance. So if I take a piece of copper, which is, say, from a copper pipe, and I take a copper penny from back when they really were copper, and I compare the two, because of the fact that they're both, theoretically anyway, pure copper, they should have the same properties as each other. Same substance, same properties. Even if the samples come from different places, as long as they're the same substance, they should have the same properties. Substances, as I mentioned a moment ago, can be classified, though, as either elements or compounds. Chemical elements are the sort of the fundamental building block of chemistry. The chemical elements, there are about 120 of them, and something like 92 or 95 of them, I think, occur naturally, and the rest are made in the laboratory. And they are substances that are found in the periodic table. So if it's in the periodic table, it's an element. If it's not in the periodic table, it's not an element. And they're substances that can't be broken down into any simpler substance by chemical reactions. Again, nuclear reactions are kind of a different area. That gets into physics, which can get kind of weird sometimes. But in chemistry anyway, you can't change one element into anything smaller and simpler. And that's essentially what the medieval alchemists spent about 500 years trying to do, and they never actually managed to do it. But they found a lot of other useful information along the way. So like I said, the elements are what you find in the periodic table, and some of the chemical elements that you may be familiar with would include things like hydrogen, oxygen, nitrogen, sodium, iron, copper, gold, silver, arsenic, lead, chlorine, and a lot of others. Actually, we getting a little ahead of ourselves on this, but it turns out a vast majority of the chemical elements are metals. A vast majority, which is interesting. Compounds, and actually elements, if you do break them down into something simpler and smaller, what you get would be subatomic particles like protons and neutrons and electrons. And subatomic particles are exactly the same no matter what element they come from. You know, so if you take an electron from hydrogen and an electron from lead, you would not be able to tell the difference between them. So the smallest unit of a substance that has unique properties would be an element. Okay, compounds are can be broken down through chemistry into simpler substances, i.e. elements or smaller molecules or smaller compounds by chemical reactions. And a compound is made up of two or more different elements, and that part is important. The elements have to be different in order for it to be a compound. If you have, say, two atoms of an element bonded to each other, and it's the same element for both of the atoms, then it's still an element, not a compound. Okay, so it's made up of two or more different elements. There are literally tens of millions of compounds known, and probably tens of millions of more compounds out there that are not known. Many of them are naturally occurring. Some of them are made in the laboratory. And like I said, tens of millions have been isolated or synthesized and characterized. But there are probably tens of millions of more compounds out there in nature that we haven't isolated and characterized yet. And theoretically, there are probably tens of millions more compounds that could be synthesized in the laboratory and just haven't been yet. And so it's interesting that we have only about 120 elements, and only about 100 of the elements are of any practical use. The ones that are synthesized in the laboratory only exist in tiny little quantities for a fraction of a second. So they're not really of any practical use. So you can take those 100 elements or so that are of practical use and combine them in ways to make tens and tens of millions of compounds. It's sort of like the way that you can take the 26 letters of the English alphabet and make hundreds of thousands of words out of them. So it's kind of a similar idea. And so some well-known compounds would be things like water, carbon dioxide, iron oxide, better known as rust, sucrose, that is table sugar, sodium chloride or table salt. Those are all compounds. It's important to remember that the properties of elements generally change significantly when they form compounds. So if you look at water, and I'm writing some chemical equations here, which is getting a little bit ahead of ourselves. So if you don't know what all of this stuff means, don't worry about it yet. But I'm just illustrating that when you form water, which has the formula H2O, you're combining hydrogen and oxygen. The properties of hydrogen and oxygen are very different from the properties of water. Hydrogen is an explosive gas. Oxygen supports combustion or explosion. And when you chemically, not mixing, but when you chemically bond hydrogen and oxygen together, you get a liquid that puts out fires. So that's a big, big change. Sodium chloride, table salt, is made up of a combination of sodium, which is an extremely reactive metal, so reactive that when you expose it to moisture, it sometimes explodes. And chlorine, which is a very highly reactive and very pungent smelling gas, which, if you inhale pure chlorine, it'll burn your lungs out. Combine those together, you get table salt. Very different compound. Glucose, the sugar in our blood, is made up of carbon, which is like graphite. That's carbon right there. Hydrogen, the explosive gas, and oxygen, the gas that supports combustion. Combine those together, you get a white crystalline solid that tastes sweet. So again, when you bond elements together to form compounds, the properties end up being very different. Okay. Any compound will have the same composition and the same properties no matter where it comes from. So pure water will be the same as any other pure water. And it doesn't really matter whether you're buying it from like distilled water in a jug from Wegmans or whether you're distilling water in a distillation apparatus at home, it should have the same properties because it's water. And it will have the same chemical formula as well. Okay. Now, as opposed to pure substances, we have impure substances, or in other words, mixtures. It is possible for you to take different elements or compounds and put them together in the same container so that they kind of coexist in the presence of each other without being chemically bonded to each other. So if you chemically bond atoms together, you're forming a compound. But if you just take a bunch of atoms or molecules and just sort of sit them next to each other, that is a mixture. Now, when you have a mixture, you can have a homogeneous mixture or a heterogeneous mixture. And we'll get into that in a moment. But anyway, a mixture is a sample that contains more than one type of atom or molecule. In other words, more than one element or compound. The proportions of the substances present in a mixture can always vary from one sample of the mixture to another. So if you've got, say, salt water, which is a mixture of salt and water, obviously, you could have, and it's also commonly known as saline solution, you could have 5% saline solution, or you can have 10% saline solution. 10% saline solution is twice as salty as 5%. And you can have a bunch of other percentages also. So, the amount of salt and the amount of water can vary from one sample to another. The question is, can the amount of the different substances present vary within each sample? And for salt water or saline solution, the answer is no. But for certain other mixtures, the answer will be yes. So the proportions of the substances present can always change from one sample to another. The question is whether the proportions can change within a single sample. And also mixtures can be separated by physical means. Physical means would be something like distillation, where you separate two substances based on different boiling points, but they're still the same substances when they come out separately as they were when they went in together. You're just taking them apart from each other. Or filtering. If you have a mixture of sand and water, you can just pour it through a filter, like a coffee filter, and the sand will stay on the filter and the water will go through. So no chemical reactions are necessary to separate a mixture. If you want to separate a compound into elements or smaller compounds, you would have to use chemical reactions. And that's because when you combine elements into a compound, you're connecting them through chemical bonds. Okay, so chemical reactions are necessary to break chemical bonds. But in a mixture, the substances are just sort of there in the vicinity of each other. They're not chemically bonded together, so you don't need chemical reactions to get them apart. Okay, a heterogeneous mixture is a mixture where the properties or proportions can change within a single sample. Heterogeneous mixtures are made up of mixtures where the components do not mix evenly at the level of individual atoms or molecules. It may be the case where you've got particles that are bigger than individual atoms or molecules, like trying to mix, say, salt and sand together, or salt and sugar for that matter. Each particle of salt or sand or sugar, as the case may be, is made up of billions and billions and billions of individual molecules. And so there's no way that you're going to be able to get solids to mix together at the level of individual molecules if you're trying to mix them together as solids. It is possible to get them to mix together evenly if you melt the solids and mix them together as liquids and then let them cool and become solids again. But if you're mixing them together as solids, a mixture of solids will basically always be homogeneous. So the composition of a heterogeneous mixture can vary within a sample as well as sample to sample. Again, if you have the mixture of salt and sand, it's entirely possible that within a given container, there might be more sand at the bottom and more salt at the top. They probably, in fact, they probably won't mix evenly. So an example of heterogeneous mixtures might be something like oil and water. If you try to mix up oil and water, no matter how much you stir it, the moment you stop stirring it, they're going to separate. And even while you're stirring it, the oil is present in little globs within the water. It's not mixing evenly even while you're stirring it. And so once it settles, you'll have the oil layer at the top and you'll have the water layer at the bottom. So at the top, there'll be mostly oil and only a little bit of water. And at the bottom, it'll be mostly water and only a little bit of oil. And that's what we mean by heterogeneous. Some other heterogeneous mixtures would be things like salt and sand, like I mentioned, or salt and sugar, if you mix them together as solids. Rocks are heterogeneous mixtures. You can often look at a rock and actually see little blotches of different colors, and that's different minerals that are present within the rocks. And if the if the blotches are big enough for you to see, then that is definitely a heterogeneous mixture. Salad dressing, it always has little glops of chunks and stuff in it. Dirt is a heterogeneous mixture. And sugar in iced tea is usually a heterogeneous mixture because in iced tea or anything cold, like a cold cereal, most of the sugar doesn't dissolve. It ends up falling right to the bottom. So you have a sugary layer at the bottom, and then you have some sugar dissolved in the layer of liquid above. That is heterogeneous. On the other hand, a homogeneous mixture, which is also known as a solution. We use the word solution in chemistry a lot, and that is just another term for homogeneous mixture. That's a mixture where the components do mix evenly. So the composition in a homogeneous mixture will be the same throughout each sample, but can still be different from one sample to another. If you have something like salt water, it will be equally salty at the top as it is at the bottom. But a different sample of salt water could be even saltier. That's entirely possible. So homogeneous mixtures could be salt water, air. Air is a mixture of different gases, and gases always mix homogeneously. And so the air has the same percentage of oxygen and nitrogen in one part of the room as it does in the other part, in any other part of the room. Metal alloys. Metals are solids, of course, but this is a case where, like I was saying, you can get solids to mix together homogeneously if you melt them and mix them together while they're liquids and then let them cool. And that's how they form metal alloys. Brass is for instance, brass is a mixture of copper and zinc, mostly copper with some zinc. You can never get copper and zinc to mix together homogeneously as solids, no matter how finely you file them down. The particles will still contain billions and billions of atoms of copper or zinc. What you can do, though, is put them in a furnace and melt them down and then pour them together and mix them up while they're liquids. Melting them into liquids has the effect of separating the individual atoms from each other, and it allows the copper and zinc atoms to mix together evenly at the level of atoms. And then if you cool it down, if you do it right, they won't separate, and you will have an alloy, which is a homogeneous mixture of solids. Sugar in hot tea would be a homogeneous mixture because sugar dissolves much better in hot water than it does in cold water. If you put sugar in hot tea, unless you use a really huge amount of it, it's all going to dissolve in the tea, and the tea will be equally sweet at the top as it is at the bottom. Gasoline is another example of a homogeneous mixture. It's several different organic compounds mixed together. They all mix together evenly. And so, they would have the same proportions throughout the entire sample for gasoline. There's a chart in the textbook for characterizing pure substances versus mixtures. It's on page 19. You can look at the full version. There's more written in than I've written in here. But anyway, for the overall subject of matter, you've got mixtures versus pure substances. If it's a pure substance, that means there's only one type of element or compound present. If it's a mixture, that means there's more than one type of element or compound present. If it's a mixture, it could be heterogeneous or homogeneous. If the components in the mixture mix together evenly throughout the entire sample, and the properties are the same throughout each and every sample, but they could still be different from one sample to another, then that would be homogeneous. If the properties are different within each sample, as well as from one sample to another, then that would be heterogeneous. For the pure substances, if it's a small, simple substance that cannot be broken down by chemical means into anything smaller or simpler, then that is an element. Also, if it's in the periodic table, it's an element. And if it's a pure substance that can be broken down into smaller, simpler substances through chemical reactions, then it is a compound. Okay, so that's a summary of that. You can look at it in more detail on page 19 if you want to. We now come to the concept of atoms versus molecules. We probably won't get through all of this before I have to call the time on this segment of the lecture. So we may review a little bit of this in lecture on Tuesday. But anyway, atoms versus molecules. Atoms, the word atom comes from the word atomos in Greek, which I've done my best to write out in Greek there, which literally means cannot be cut or can't be subdivided. And that's because atoms are the smallest building block of matter. Atoms are the smallest unit of a given substance or a given element that have the same properties as that element. If you break it down any further than the level of atoms, then again, you're getting subatomic particles like protons and neutrons and electrons, and they are all the same as each other. In other words, a proton from hydrogen would be the same as a proton from iron. An electron from oxygen would be exactly the same as an electron from lead, and so on. All right. Atoms can combine with other atoms to form molecules. They do this through chemical bonding. If atoms are just sitting next to each other without a chemical bond between them, then what you have is a mixture, not a bond. Unless they're atoms of the same element, then you would just have an element. But if atoms are connected by chemical bonds, then you have a molecule. Most of the elements are found in nature as individual atoms, except there are certain elements that are known as diatomic elements. Diatomic just literally meaning two atoms. And what that means is that certain elements are found in pairs in nature. And some of these are some of the most common or most important elements like nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Those are nitrogen, oxygen, and chlorine especially are pretty important elements. And so whenever you find them in nature, you find them as pairs. So the symbol for nitrogen is N for nitrogen. But if we just say nitrogen, then we're referring to nitrogen the way it's normally found in nature, which is in pairs. And so we put a little 2 after the N to indicate that these are two nitrogen atoms bonded together. If we want to talk about just N, that is just one atom of nitrogen, that's such an unusual thing that we would normally refer to it explicitly as nitrogen atom. So when we say nitrogen or any of these other elements, we are implying as it's found in nature. So nitrogen would be N2, oxygen would be O2, fluorine would be F2, chlorine would be Cl, that's the symbol for chlorine, with a 2 after it. Bromine would be Br2, and iodine would be I2. So again, if you want to talk about an oxygen atom, you would explicitly say oxygen atom, and the symbol for that would be just O. But the thing is that these elements, these atoms, individual atoms of these elements are unstable alone. And if you put a bunch of nitrogen atoms in a container together, they will immediately start pairing up. And you will end up with N2 within a fraction of a second. Okay, as I mentioned, the existence of atoms was first theorized by Democritus about 2,500 years ago. Unfortunately, some guy named Aristotle disagreed with him, and Aristotle is like the Bigfoot of philosophy. Nobody contradicts him. So that set back science by about 2,000 years. We eventually found that atoms really do exist. The first real scientific theory postulating the existence of atoms and what they were like was developed by John Dalton around 1800, so a little over 200 years ago. And it's gone on, and the theory of atoms has developed from there. Atoms are very small. Atoms in size are on the order of about 1 angstrom. An angstrom is a sort of a special metric unit that's used in chemistry and physics because it's about the size of an atom. 1 angstrom is about the size of a typical atom. An angstrom is 10 to the minus 10 meters, or 0.000000001 meters. And for comparison, if you're not that familiar with the metric system, a meter is about the size of a yard. So think of taking a yardstick and dividing it into 10 billion slices. An atom would be about the size of one of those slices, 1/10 billionth of a yard. And so we're dealing with stuff here that's very, very, very small. On the other hand, if you have any kind of appreciable amount of a substance, that's going to involve an absolutely enormous number of atoms. So if you have, say, 12 grams of carbon, which is about ½ ounce of carbon, say in the form of graphite, you've got a bunch of pencil leads. We call it lead, but it's actually graphite, which is carbon. You've got a bunch of pencil leads in your hand, and collectively they weigh about ½ ounce. The number of carbon atoms in that amount of graphite would be this number here. And I'm not even going to say it because in scientific notation, it's 6.02 times 10 to the 23rd power. But yeah, as you can see, that is a really, really big number. For a fairly small amount of carbon, you could easily hold that in your hand and it would weigh practically nothing, just ½ ounce. Actually, a little less than ½ ounce. Most elements, I think, as I mentioned before, most elements are found in nature bonded or combined with other elements, often oxygen, in compounds. And we then have to go through a process of breaking down the compound into its elements if we want to get, the pure elements. And I'm over time again. Sorry about that. So I'll draw the line there, and we'll pick up there on Tuesday. Okay, I'll see you then.